Good morning, dear students. Today we are going to discuss about third law of thermodynamics. Third law of thermodynamics can be explained on the basis of Nernst heat theorem. It was postulated by Walther Nernst. Consider Gibbs-Helmholtz equation, that is delta G is equal to delta H plus T into dou by dou T of delta G at constant pressure. When temperature T equal to 0 Kelvin, delta G will be equal to delta H. This is the basic equation of Nernst heat theorem. Another scientist called Richard made an observation during his experiments on the EMF of cells at low temperature that the quantity dou by dou T of delta G at constant pressure decreases with the decrease in temperature. Then delta G and delta H approach each other more closely. Then according to Nernst, he also suggests that the value dou by dou T of delta G at constant pressure approaches 0 asymptotically as the temperature is lowered towards absolute 0. This statement is known as Nernst heat theorem. Asymptotical nature is its limiting nature of the function. This can be explained from this curve. Here delta G or delta H versus temperature curve. This is the curve of delta G and this is the curve of delta H. Their values approach each other asymptotically in the vicinity of 0 Kelvin. This statement can be mathematically expressed as limit T tends to 0 dou by dou T of delta G at constant pressure equal to limit T tends to 0 dou by dou T of delta H at constant pressure equal to 0. Then let us consider the two equations of great significance in thermodynamics, that is dou by dou T of delta G at constant pressure is equal to minus delta S, that is from second law of thermodynamics, and dou by dou T of delta H at constant pressure is equal to delta Cp, that is our Kirchhoff's equation. Introducing these two equations in these limiting equations, we get results that limit T tends to 0, delta S equal to 0 and limit T tends to 0, delta Cp equal to 0. That is near to 0 Kelvin, any process should occur without change in entropy and without change in heat capacity at constant pressure. When we applied these two equations to a chemical process, this means that the products and reactants have same heat capacities at 0 Kelvin. That is, we know that delta Cp equal to Cp of products minus Cp of reactants. That is, all the substances have same heat capacity at 0 Kelvin. From the applications of quantum theory to this heat capacity of solids, we can say that heat capacities of solids should tend to be 0 at 0 Kelvin. That is, we can write limit t tends to 0, Cp equal to 0. This is an extension of heat theorem. Now consider this equation, that is limit t tends to 0, delta S equal to 0. When we applied this equation to a chemical process involving solids, this means products and reactants have same entropies. And this leads to a suggestion that all solids should have same entropy at 0 Kelvin. So, Nernst heat theorem leads to the formation of third law of thermodynamics by Max Planck, that for pure solids entropy reaches 0 at 0 Kelvin. That is our third law of thermodynamics. Nernst heat theorem is not applicable to gases because they do not exist at 0 Kelvin, and it is not applicable to liquids also. So, third law of thermodynamics apply only to solids. Then what is the physical significance of the statement of third law of thermodynamics? We know that entropy is a measure of disorder present in a system. At 0 Kelvin, all the molecular motions will collapse. Then a perfectly crystalline solid has perfect order of its constituent particles. That is, there is no disorder at all. This means that its entropy is 0 at 0 Kelvin. That is, at 0 Kelvin temperature, there is no disorder, which means entropy will be 0. Now consider the importance of third law, that is determination of absolute entropies. What do you mean by absolute entropy? When the substance changes from its site to any other state, the finite positive entropy, that is our absolute entropy, that it possesses in the new state, will be equal to the entropy change that occurs during its transition to the new state. So, third law of thermodynamics used to define absolute entropy of a substance in a specific state as the entropy change associated with the transition of a sample of a pure substance from 0 Kelvin in a perfectly crystalline form to some specified state is called absolute entropy of that substance in the new state. But for an actual crystal, there may not be perfect order even at 0 Kelvin, so that its entropy is not 0 but a finite value at 0 Kelvin. That entropy is called residual entropy. That is an actual situation or practical situation. We know that perfect crystalline substance is an imaginary matter. Next is determination of absolute entropies of substances like solid, liquid or gas at any temperature at a constant pressure. An infinitesimal entropy change, that is ds, of the system is given by ds is equal to dq by t. And we know that the molar heat capacity C is equal to dq by dt, or dq is equal to C into dt. If we consider the system at constant pressure, we can write dq is equal to Cp into dt. Then apply this equation. In this equation, we can write ds is equal to Cp dt divided by T. Then according to the third law, the absolute entropy of a perfectly crystalline substance is 0. So we can integrate this equation from 0 Kelvin to T Kelvin. And at 0 Kelvin, entropy is 0. At T Kelvin, entropy is a specific entropy that can be represented by St. So integral 0 to St ds is equal to integral 0 to T Cp divided by T into dt, which is equal to St equal to integral 0 to T Cp into d of ln T. This integral, that is the integral for St, the absolute entropy of the crystalline solid at T Kelvin, can be evaluated from the area under the curve of a plot of Cp versus ln T in the temperature range 0 Kelvin to T Kelvin. And this calculation is for a solid substance, and that does not involve any transition reaction, that is change from one crystalline to form into another crystalline form. If such a transition is involved, then the entropy change for that transition, delta S transition equal to delta H transition divided by 2 T. This equation will also have to be considered in the calculation for the transition reactions. Now consider the determination of absolute entropies of liquids and gases. The total absolute entropy of a substance in liquid or gaseous state at T Kelvin at atmospheric pressure can be taken as sum of the all the entropy changes that occur during its transformation from the crystalline state at 0 Kelvin to the current state. So it involves different steps. First one, the Cp values for the substance measured at various temperature range from TF Kelvin down to as low temperature as possible. Here TF represented its fusion point, that is STF equal to delta S1, which is equal to integral 0 to T Cp of solid, that it can be represented by the letter S d ln T. This entropy calculation can be done from the area under the curve of a plot of Cp of solid versus ln T in the temperature range 0 Kelvin to TF Kelvin. Here delta S1 is calculated below the temperature of fusion point. Then the substance is heated at its fusion point TF to convert into liquid state then the entropy of fusion of the substance, that is delta S2, will be equal to delta H fusion divided by Tf. And then if it is the absolute entropy of the substance in its liquid state at T Kelvin, that is to be determined, we have to do another final step for the calculation of absolute entropy. That is, the liquid is heated from Tf Kelvin to the temperature T Kelvin. That is delta S3 equal to integral Tf to T Cp of liquid into d ln T. From its Cp values determined in this range, the entropy change in this process can be calculated. So, the absolute entropy of the liquid at T Kelvin will be equal to St of L equal to delta S1 plus delta S2 plus delta S3. Then if we want to calculate the absolute entropy of the substance in its gaseous state at T Kelvin, then step 3 is done as like delta S3 dash. That is, the liquid is heated from Tf to Tb, that is our boiling point. From its Cp values determined in this range, the entropy change delta S3 dash in this process can be calculated. That is delta S3 dash equal to integral Tf to Tb Cp of liquid into d of ln T. Then the liquid is heated at its boiling point Tb to convert into its gaseous state. Then the entropy of vaporization of the substance will be equal to delta S4 equal to delta H vaporization divided by Tb, where delta H vaporization is the molar enthalpy of vaporization of the substance. Then gas is heated from Tb to the required temperature T Kelvin. From its Cp values determined in this range, the entropy change delta S5 in this process can be calculated. That is delta S5 is equal to integral Tb to T Cp of gas into d of ln T. Then the absolute entropy of the gas at T Kelvin will be equal to delta S1 plus delta S2 plus delta S3 dash plus delta S4 plus delta S5. That's about third law of thermodynamics. Hope it is clear. Thank you.